now. I don't want to keep you away too much from dinner. Let's use this to talk a little bit more about this copper chemistry. We do this already anyhow in a tutorial style, and I would like to just give you some more ideas on this type of chemistry. So one thing we realized when we did this chlorosulfonylation was that it didn't matter if we use the copper-2 catalyst or the copper-1 catalyst as a precursor. It's a copper-1 photocatalysis for sure, because we need to reduce the sulfonyl chloride. So we need to do copper-1, which then forms copper-2, and it's not feasible that we use copper-2 to copper-3. That has essentially no reduction power. But we could use the copper-2. You see here we have the copper-1 complex, here we have the copper-2 complex, and it didn't matter which we would use. We could use both, and you can see here in blue we have a lot of substrates. Blue are the yields for the copper-2 complex, and in this reddish pink color is the copper-1. And in some cases we have even better success with the copper-2 complex. And so the question, of course, is why? Why are we getting these? Why can we do this with copper-2? And the answer to this is obviously we must be forming copper-1. How do we do this? Because we don't have a reductant present, and we have nothing which we can oxidize and do this. So one of the answers to this could have been is that if you irradiate the copper-2 chloride complex, that you do a homolysis, and when you do this homolysis, you're forming a chlorine radical, and you form the copper-1 complex, and the copper-1 complex is your active ingredient. And so what is the chlorine radical doing? Well, under the conditions which we have, it probably abstracts from something, maybe from the solvent or so, maybe abstracts a hydrogen. Again, when we try to publish this, the one reviewer said, tell us what the chlorine radical is doing, and we said, we are only using this in 1 mole%, so it just forms a little bit and probably is lost in the solvent, and we were okay that we didn't have to chase after this. But I will show you in the end that we pretty much know what such chlorine radicals can do. And we are definitely not the first one. As always, there's nothing new. There's nothing new under the sun, but this gave us more or less this the idea that we can activate substrates by taking a metal complex where we have the ligand coordinated to this, and if this gets irradiated and a homolysis might occur, then we are also having a starting point for radical chemistry. And this is a process which is probably initiated in most cases by ligand metal catalysis. So you have your metal catalyst, and then your ligand. In this case, you see you can look at this from this here. The ligand gives 1 electron to the metal, and then this way it forms. Then if the bond splits, it forms the radical and the reduced metal. And so this is something we wanted to explore further, and actually I show you the first example. I'm not chronological here, which we actually explored already 6 years ago or 7 years ago by now. But this idea that we can do this homolysis. We like to call this visible light homolysis, or now if you do it at UV, you can also call it light-induced homolysis, that a metal substrate complex might, under irradiation, split into the radical and the reduced catalyst. And that is you will see that's a pretty interesting activation method from one point of view. And that is, we wanted to know more about this homolysis process. And so we teamed up with a group of Phil Castellano. He's in the United States. And he's a really expert in transient spectroscopy. And so when you do transient spectroscopy, you can, on very short time scales, you can see how species are changing, and if you get like go from a copper 2 to a copper 1 complex and so on. So what we did is we sent him as a reference one of our copper 1 complexes, and he measured the transient absorption spectrum, and this is what you see here. And so what he did is he took the copper 1 complex in acetonitrile and simply excited this at 470 nanometers, and this is the spectrum he get. And then we gave him the copper 2 complex, and then he irradiated this again, and he's irradiating with an 80 femtosecond laser, so extremely short pulse. He irradiated the copper 2 complex, and this is the spectrum he got. And I'm not sure if you have seen transient spectroscopy, transient spectra before this, but you see here you have the irradiation of the copper 2 complex. Here you have the reference of the copper 1 complex. So let me tell you what's the difference. What's the difference between these two diagrams? So the question is up now. So I give this again to you. And so if you want to interpret these spectra, this is copper 1 reference, this is irradiation of the copper 2. So what would be your feeling? How should you, and I had the same thing. I never interpreted or looked at such spectra, and I had also didn't know anything about this. And so Phil Castellano, he just sent me these spectra. And so what's your feeling? What do you think is different here between the left and the right diagram? Oh, yeah, this here. Let me see if you have already answers. No answers yet. Don't be shy.
Red line.
Sorry?
The red line is different.
Red line looks a little different here, yeah. Mm-hmm. No answer so far, because you all don't dare probably to say the obvious. Still no answer. It's like a quiz, right? Sometimes you have this in the newspapers. They give you two pictures and they say spot the difference. Huh. You see, I was more open about this. I had no problems to call Phil and say, you know, Phil, I don't understand anything about transient spectroscopy, but for me, these two spectra look exactly the same. I don't see the difference. This is chicken soup effect here, right? But look at all this, right? This looks exactly the same. I said, Phil, you sent me the wrong spectra. You need to send me, you mixed it up, you sent me twice the same spectra. And he said, no, I didn't. Everything was okay. But he said, you know, when we irradiated the copper 2 complex, all we see is copper 1. We do not see the copper 2 signature. And that is in a way really exciting, because that means if you, on the time scale of 80 femtoseconds, let's say 100 femtoseconds, if on a time scale of 100 femtosecond, the copper 2 has completely converted to copper 1. This means that excited state lifetimes do not have to be high nanosecond or even microsecond. This means that picoseconds or so might be sufficient. And so the difference to all the other chemistry we said, there we had an outer sphere electron transfer. We had the excited state, and then we are transferring somehow the electron to a substrate, or we're taking it. But here, the substrate is already coordinated to our photocatalyst. And this way, then, suddenly these processes become very fast. So on a time scale of 100 femtosecond, this dissociation has occurred. And so that is what we think is, and you say that the spectra doesn't look anything reasonable, but we got a pretty decent paper out of this for showing the same spectra, because I think the interpretation really is correct here, that we are essentially on less than a picosecond do this homolysis reaction. And this means, of course, that if you can go through this activation mode, that excited state lifetimes, even on complexes like iron, which typically have picosecond lifetimes, that this becomes irrelevant and that it's suitable for photocatalysis. And so with this, we are really pretty excited about this. I would like to point out that, again, the group of Kochi, chemist from Japan, really one of the absolute pioneers and heroes, and he, not only on photocatalysis, Kochi did essentially, I think, everything in catalysis. He already noticed that under UV irradiation in 1962, under UV irradiation with copper-2 chloride, and he is adding lithium chloride to this, so he's making probably such an anionic copper chloride, copper Cl3 minus complex, that under UV irradiation, he noticed that this splits off a chlorine and makes a chlorine radical. And Kochi already was able to show that you can do chemistry with this chlorine radical. So you could do, for example, do a hydrogen abstraction and do a benzylic halogenation. You could do a hydrogen abstraction here and do an allylic hydrogenation. You could do addition to double bonds and get these type of chlorinated compounds. And so more recently, the group of one showed again that you can do this under visible light. You can do exactly this type of chlorine addition. And I think more exciting, the group of rovers showed that you can do, after you do the hydrogen abstraction to get a radical here, that you can trap it again with alkenes and do carbon-carbon coupling reactions. So our first contribution to this came already in 2018, and there we showed we wanted not only to have the halogen radicals and do hydrogen abstraction. We were wondering, can we get different radicals and do other type of chemistry? And so one thing we did is we were looking at azides, and so we are making copper azide complexes. And again, sure enough, if we irradiate this, we are forming azide radicals, and we could use this in order to make such azido-ketonization. So you see, we're doing a type of an atom transfer radical addition. We are adding the azide radical to this position, but then, very importantly, we are transferring oxygen into the product, and we have to do this reaction under air. That is something, maybe we do it tomorrow at some point. A thing I wanted to point out in the tutorial as well. I can show you why we need the air. If you look at the mechanism, and again, it always comes to the question, how do we close catalytic cycles? And so if we start with copper-2, this is where we start, we make the copper-2 azide complex. If we irradiate this, we are making the azide radical and copper-1. And the azide radical can add to the alkene, we form a new radical. And now is the question, how do we get back the copper-1 to the copper-2? And the copper-1 is not really a very strong reductant to reduce this and then form copper-2 again. So what we need in this reaction is we need oxygen. And oxygen very efficiently traps these type of radicals, and then at the same time reoxidizes the copper-1 to copper-2. And so what we believe is that this radical trapping is extremely efficient. Whenever you do such type of reactions, You need, normally, if you don't want to have the oxygen in there, you need to do it under exclusion of oxygen. If you have oxygen in there, you do exactly this. But we needed this because only this peroxo radical is now able to recombine with copper 1, and this way reoxidize us the copper to copper 2. And then you can now see here, if I do now a formal elimination of copper hydroxide, I take out this proton, form the double bond here, and then I get copper hydroxide back. This is how we are getting the product, and close the cycle. So in quite a number of more reactions, which I will show you, is we can always add a radical, which we get from such a homolysis event, but then we are getting the carbonyl group into this. I would also like to show you how you can analyze such chemistry. So one thing, of course, which is nice is azide, of course, is a fantastic ligand to do IR spectroscopy. So we looked at we could see that we are forming a copper azide complex by looking at the azide band in the IR, and that is significantly shifted compared to the azide which you, for example, have in the TMS azide. UV absorption, of course, we saw a significant shift in the UV once we exchanged the chloride for azide. And then, of course, copper 2 complexes are EPR active, right? Because it's a radical. And so with a radical, you can do EPR spectroscopy. And so we could make the copper azide complex. And so here in yellow, we had the spectrum, and then we started irradiating this. We are forming copper 1, which is of course not EPR active any longer, and so then the signal went down because we were now making the diamagnetic copper 1 species. And so that was our first contribution to this. And then we, of course, as it is, if you find out that things like this might work, you try other type of compounds. And so here we tried malonate. You might remember that we already saw this with a manganese acetate this morning, that you can oxidize the malonate to the malonate radical. And this is exactly what we can also do with copper 2. So we take malonic ester in the presence of a copper 2 complex, and what we probably form is such a malonate copper 2 complex. And if this gets irradiated, we are cleaving the bond. We are forming copper 1 and the radical, and then this radical adds to the alkene, to styrene here. So we are forming this new radical, and as you have seen in the previous example, we need the oxygen to trap this radical and reoxidize the copper 2, and then this way we are getting the oxoalkylated compounds here. So we can take vinyl arenes, and we add the malonate group here, and again the carbonyl group here. So the question is, if we would have a photocatalyst which would be a better reductant. So as I said, copper 1, to bring it back to copper 2, copper 1 is not a very good reductant. It has a very low reduction potential. But if we would use a photocatalyst which could do this more efficiently, do the reduction, could we change the course of the reaction? And this is exactly what we did. We used one of these organic dyes here, this 4-CCIPN, and that is in the excited state, can also oxidize it. So we are again forming the malonate anion, and we can oxidize it to the malonate radical. So you see this is the very same type of radical here. It adds to the alkene. This is also still the very same. But now we have the reduced photocatalyst. This is what we had here too. The copper 1 is the reduced photocatalyst, but the reduced copper 1 is not able to reduce this radical to the anion. But the reduced 4-CCIPN can do this. So now this radical gets reduced to the anion, and it can pick up a proton. And so we are running this reaction under inert gas atmosphere. We are running this reaction under oxygen. If we run with the 4-CCIPN, for some reason we don't completely understand. If we run this under oxygen, we're getting no reaction. If we run this under nitrogen, we're getting no reaction. But with the copper combination oxygen, you're getting oxoalkylation. With the combination of nitrogen atmosphere and 4-CCIPN, we're getting hydroalkylation. And I think that's also pretty exciting that we have the same starting materials, but just by changing a catalyst, an oxygen atmosphere, or different catalyst and inert gas atmosphere, we can get different products out of this. And so we call this like a divergent and synergistic photocatalysis. And you see here we are picking up a proton. That's of course the easiest electrophile which you have around. But we could also see that if we have already one of these oxo-alkylated products, if we are forming now the anion, rather than picking up a proton, we can also do use as an electrophile a carbonyl group and get these type of products. And this is something we use in order to make a cyclopentanol here. And so by now there's quite a bit of these copper 2 substrate chemistry where you can use a copper 2 substrate complex and do homolysis. We have recently reviewed this, so again, if you want to know more about this, this has become a really popular area. I would like to show you one more example where we bring together copper 1 and copper 2 chemistry. And I already pointed out earlier that you can make the same radicals from different starting materials, either by a reductive pathway, that is, in this case here, we're using a bromonitroalkane, where we transfer an electron to and reduce the substrate, and making such a radical, nitroalkane radical, and that goes along with that copper 1 is becoming copper 2 here. And so we're forming this type of radical. So this is essentially this radical. We think we're getting chemistry out of this. But you can do the same thing from not starting the bromonitroalkane. You can do the same thing from starting from the nitroalkane. And now it's the same idea. You're making with the base, you don't need, for nitroalkanes, you don't need strong bases. They're already very acidic. You form the anion. And now this anion, and we do this in the presence of copper 2, and the copper 2 is now, if this is doing the homolysis, forming this nitroalkane radical. And the difference is now that we have copper 1 present, and the process up here we had copper 2 present. But we have essentially the same type of radical intermediate, and we were wondering what happens if we react this with alkenes. And is there a difference in which way we have generated this alkene? And in fact, there is. I would like to point this out. There was already, before we started this, there was a publication which did the same thing with iridium. And what they found is that normally you would think in all these ATRA reactions which we had discussed is that you should be able to make the radical here and then in the end add the nitroalkyl group and the bromine group across the double bond. And as you can see here, this didn't work very well with the iridium catalyst, and instead they're getting such kind of heterocycles out of this. And they were able to explain this. They said, well, we are forming the radical by having an iridium-3 catalyst, which is able to reduce this, forms the iridium-4 catalyst, makes this alkyl radical. And this alkyl radical adds to the styrene and it forms this radical. But this radical can do a cyclization onto the nitro group. And this way it can form this radical here. And this is a very good process because this radical is very close to what we all know as tempo. It's a persistent radical. So that is a pretty good, good case. And so therefore, this radical had a high tendency to do this. And again, we were thinking, if we have copper 2 present, would we be able to trap this radical? So would be the cyclization faster or would be the trapping faster? And if the trapping would be faster, we should be able to get this ATRA product rather than the type of cyclization product. And let me see, if you look at this here, this cyclization, and that's really relatively facile, but in terms of Baldwin rules, let me know what type of cyclization this is. So if I have this here, let me go back to here so that you can look at the cyclization, right? If this cyclization cyclizes onto the nitro group, what is it? What is it? Is it working? Mm-hmm. 5-exo trick. One brave answer so far. Okay. 2 brave answers so far. Now the crowd is following. Yes, it's a 5-minute ring, but always keep in mind Baldwin ring closure qualifies, you need to say the ring, which center is involved, and if the bond which is breaking breaks inside the ring, that is 5-endo or endo. If it breaks outside the ring, it's exo. So, okay, 6 exo tricks. I can see it's getting late, right? Because I can see that some people have now problems to count the number of atoms in the ring. Let me show this to you again, right? It's clearly a 5-minute ring, right? So 6 exo is probably out of the question here. And so, okay. So the one thing you apparently have problems with is to decide, is it exo or is it endo? So look at this. This radical closes here, forms the ring, and the NO double bond needs to break. So it's an endocyclization. It's a 5-endo trick. And that's the one thing we said, is that 5-endo trick is probably not a good cyclization. But again here it's radical, early transition states. So you can see that this is still feasible. And it is feasible if you do this with iridium apparently. But we thought that it might not be so completely fast that with copper 2 we might be able to trap it out. And this was indeed the case. We've been able to do, again, in a very, very broad way, we've been able to get the ultra products because apparently the copper 2 is able to trap that radical efficiently. And so, again, what you could do is, we were able to show that if you do the chemistry with iridium, you indeed see the cyclized radicals here. The radicals which were not proven by Oy, but they were proposed, that this indeed is happening. So we were able to show with EPR spectroscopy that with iridium, this radical indeed, and this is the EPR spectrum for this, which proves that this is an organo-oxygen-centered radical, that this is indeed the case, and you don't see it when you do the copper catalysis. And so that is, again, why we think that the proposal we have here, that the copper 2 is able to efficiently interfere with the cyclization, and then by reductive elimination, give us the ultra product, that this is really the case. And so again, this is going to these inner sphere mechanisms. Reaction works very, very nicely, and we think also it's a relatively useful compound reaction, because with these compounds you're generating a bromo and a nitro group in such a 1,3 relationship, and all you need to do is add a base, and then if you add the base you form these nitrocyclopropanes. And nitrocyclopropanes, if you reduce the nitro group to an amine, you have cyclopropylamines, and cyclopropylamines are really very well, very broadly used in quite a number of drugs. And so we believe that this is actually a relatively useful type of compounds. And so more chemistry is in the handouts, you can look at this. So what happens if you make this nitro radical starting from copper 2? Because then in this homolysis event, you don't have copper 2 any longer present, you have the copper 1. So you're forming this radical, but there's nothing, and it can add to the alkene, but we will argue that we have no copper 2 present to trap it now. And indeed, it goes a different way, because now, indeed, the radical cyclization takes place. So we're getting this type of radical, and this radical now gets, we have here reduced the catalyst. So this now, in turn, this radical gets reduced and oxidizes back the copper 1 to copper 2. Our reaction is oxygen dependent. We need oxygen, so we believe again that the real oxidation of the copper 1 back to the copper 2 occurs through oxygen, and it's not done directly, right? You could think about that this radical could get reduced by copper 1, this way forming back copper 2 and this radical. But then the reaction should also work without oxygen, and it does not. So we think oxygen is a mediator in here. We are forming this intermediate. If this picks up a proton and eliminates water, we form these type of isoxazoles. This is like the result of a 3+2 cycloaddition. But these 3+2 cycloadditions are known, but they require temperature, high temperature. And also they do not work with 1,2 disubstituted alkenes. And again, in our hands, the scope we have here is very, very broad. And so we talked about this earlier when you said advantages of radical, of photocatalysis, that sometimes you can bring a reaction down from 80 degrees to room temperature. This is what we have been accomplishing here. But at the same time, we need light, and you can argue, is it better to do room temperature and light, or is it better to do 80 degrees and no light, right? And so that is also, I had the big discussion with my students, Naina Sadhana, who is from India, and she said, well, it's great. She already wrote the introduction, and she said, oh God, we can do room temperature, and these other people have to do temperature. I said, you need to be careful. A reviewer might see this very differently. You need to show, if you want to read it, she wants to get this in a very good journal. If you want to get it in a really good journal, you need to show that you can do something which you cannot do with a thermal variant. And so then she went back and she actually did quite a lot. And again, it's extremely broad. And indeed, what is nice about this, it works not only with activated alkenes, it works with unactivated alkenes, and especially it works with 1,2 disubstituted cyclic alkenes. And these are the alkenes which do not work if you just heat it up under the thermal protocol, try to do a 3+2 cycloaddition. And so again, this is always very important that you don't want to stop if you have a reaction, and you want to publish your paper from your PhD or master work. It's not enough that you say, oh, it works. And very often I have this discussion with my coworkers, and I say, so what? And they said, yeah, nobody has done it like this before. But the question is always, it doesn't have to be always different, but you need to be able to make a story why other conditions might be good. And here, for example, we think that we can pitch that we switch a reaction which is normally a concerted reaction, 3+2 cycloaddition, to a radical regime. This way allows us indeed to do room temperature rather than 80 degrees temperature, but also we can do substrates which were in the literature where people say with this thermal protocol it's not successful, right? And that is always something you need to, especially if you want to get this in journals like Angewandte or JACS or whatever, you need to look out for then what can I do where I can really make a point that I can do things which I cannot do otherwise, right? And in the beginning we had this discussion, and then she said, oh, and this substrate under the other conditions was reported only with 62%, and I can do 76. Again, this might be dependent on the operator. You might have a good day, you might have a bad day, right? Again, this is not enough. This doesn't drive it home. When she came to me and says, I tried this protocol with cyclooctene or with cyclopentene, and it doesn't work at all. And she has a number of other ones where she also said, it doesn't work under the other conditions. Then you have something where people will say, it's not only a different way to do it, it's not only a different mechanism, but it can do things you cannot do otherwise. Okay. And okay. We need to save this for the tutorial. I need to go over the schedule which we have with the different lectures, and then maybe we do the tutorial tomorrow morning and or the questions I had for tutorial, because I would also like to discuss some of these iron chemistry in context with the with the mechanism and closing the mechanistic cycles. So, but I think you guys all deserve dinner now, 6:30. How many hours did you hold through here? That was from 10 o'clock in the morning. I at least had a break when there was this NMR lecture on Bohr, and you guys had to sit through this here. So that's what, it's now 8.5 hours with a few tea breaks and a lunch break. So very good. So thank you very much for being so brave here and doing this, and I hope you still like to come back tomorrow, and then we talk about these things a little bit more. Okay, have a good evening. Yeah. When do we do it? Did we already do a photo? You need a, yeah, we did. Yes, yes.